Hello everyone, I'm Yu Tang from Lab Research Group at the University of Pittsburgh. Today I'm going to talk about thermal power of quantum wires at the lanthanum aluminate strontium titanate interface. The material system we're working on is lanthanum aluminate strontium titanate heterostructures. When a thin layer of lanthanum aluminate is grown on top of strontium titanate, a 2D electron liquid will form at the interface. This interface exhibits a lot of interesting properties such as tunable metal-insulated transition, tunable ferromagnetism, tunable superconductivity, tunable spin-orbit coupling, and joint and oscillating thermal power at the very low carrier density. All of these features are related to electron properties at the interface and make the interface rich in physics. In our lab, we developed a technique called the conductive FM lithography that allows us to create nano device at the reduced dimension, as shown at the interface. As shown in the figure, when 3 cells of lanthanum aluminate is grown on top of strontium titanate, the interface is insulating. However, by applying a positive voltage to the conductive FM tip, one can locally make the interface conducting and create nanowires at the interface. The width of nanowire is typically 10 nanometers, and by property reduced, the tip voltage can be reduced to 2 nanometers. This is a reversible process, therefore by applying negative tip voltage, we can erase the nanowire and the interface restore the insulating state. Through this, we can create various nanostructures such as quantum dots, quantum point contacts, or superlattices. With conductive FM lithography, we're able to create 1D nanostructures. A lot of interesting phenomena has shown in these 1D nanostructures. We can fabricate wire-based single electron transistors. In these single electron transistor devices, a new electronic phase has been discovered where electrons pair without forming superconductivity. We also found tunable electron-electron interactions. One of the most important technique advancement is the electron waveguide. In the electron waveguide, we can observe these conductance plateaus at integer values of E square H, which demonstrate the quantized Bodice transport in the electron waveguide. We also discover a new Pascal liquid phase in electron waveguide where the conductance plateaus shows up at 136 E square H, corresponding to a number series in Pascal triangle. This suggests a bound state of more than 2 electrons. From experiments on regular nanowires, we discovered the 1D nature of superconductivity at the interface where the superconducting state is situated, the boundary between the nanowire and the nearby insulating region. Here we study thermal power in the electron waveguide. First, I'd like to briefly introduce the electron waveguide. This is a typical device configuration. The electron waveguide is fabricated by bracketing a regular nanowire with 2 highly transparent potential barriers. The typical length is at the typical length of an electron waveguide is at the micrometer scale. In the device, by applying a voltage to the side gate, the chemical potential of the electron waveguide can be tuned. The conductance of the electron waveguide is quantized as a function of chemical potential and exhibits conductance plateaus at integer values of E square H. To better observe the evolution of conductance, we can look at the transconductance data by taking derivative of conductance with respect to chemical potential. Here is the transconductance as a function of chemical potential and the magnetic field. The transconductance data reveals rich subband structure which can be understood as vertical lateral modes as well as spin degree of freedom, which is in overall agreement with the waveguide description. On the right, the device configuration. In our experiment, First, we'd like to measure the electrical conductance to characterize the electron waveguide. So our electron waveguide is 600 nanometers long, and in the experiment, we source current across nanowire to measure the four-terminal conductance of electron waveguide. The four-terminal voltage is measured in the configurations between terminals 3 and 4, and we can also measure current through the electron waveguide. And the measurement is done in a low-frequency locking technique. This is the typical parameters for the excitation voltage. This is the four-terminal conductance, which is given by I1 omega and V1 omega. And I1 omega and V1 omega are the measured voltage and current AC components at the frequency excitation at the excitation frequency. On the right is the typical conductance data of the electron waveguide. The conductance of electron waveguide as a function of the chemical potential is measured at the low temperature around 80 milli-Kelvin from -9 Tesla to 9 Tesla. You can see the conductance increases with the chemical potential and shows quantized conductance plateaus at the integer values of E square h, which confirms quantized ballistic transport in electron waveguide. At some magnetic field, for example 6 Tesla, we can see the Pascal liquid phase, where the conductance plateau shows at the 136 E square h. And we can also look at transconductance data. It is so the bright area mark where the Fermi energy is crossing a subband bottom, and that a new subband is being available, and the dark area marks a conductance plateau. And in the transconductance data, we can also see the feature that some subbands lock together and separate again. This phenomenon can be explained by the attractive electron-electron interactions. So on the right is a typical conductance, is a typical is the configuration for the thermal power experiment. Thermal power is characterized by the induced voltage due to the temperature difference across the electron waveguide. The temperature difference is generated by sourcing the current on the left side nanowire of the electron waveguide, and we source current here to heat up the nanowire, and terminal 2 is floated during the process. And since the induced thermal voltage is due to the Joule heating, we measure thermal voltage at 2 omega frequency. We'll use the Mott relation to obtain the Seebeck coefficient, which is given by this equation. T is the temperature on the left, and Tr is the temperature on the right, which is in our case estimated by the experiment temperature. This is typical thermal voltage data at different magnetic fields, one at 3.5 Tesla, the other one is at 0 Tesla. As the electron waveguide becomes conducting, we can see thermal voltage compares very well with the DeLonghi mu, which suggests the electron is the heat carrier and also justifies the description of the Mott relationship. Based on the Mott relation, the temperature on the left side of the electron waveguide can be deduced from this equation we can plot here, and we can also use Mott relation to estimate the Seebeck coefficient, which is plotted here, and TL in the process is 88 milli-Kelvin. So the thermal power experiment is also studied at different temperatures. On the right, thermal power is measured at 100 milli-Kelvin and 400 milli-Kelvin at 6 Tesla. We can see that as temperature increases, the quantized conductance and transconductance are smeared out due to the thermal broadening. As a result, this thermal voltage is also smeared out and becomes weaker, but still compares very well with the DeLonghi mu. We can plot Seebeck coefficient as a function of conductance at different temperature, And we can see the Seebeck coefficient at the conductance plateau is more sensitive to temperature at the conductance plateaus than the Seebeck coefficient at the other conductance values. To further explore the temperature dependence of Seebeck coefficient at different conductance values, we pick different conductance values and plot the temperature dependence of Seebeck coefficient together. Both temperature and Seebeck coefficient are in log scale. Very interestingly, we can see Seebeck coefficient has two kinds of temperature dependence. At the conductance plateau, it's proportional to T squared, but when temperature is not at the conductance plateau, it's proportional to a square root of T. And this can also be seen when we directly plot the exponent as a function of the conductance value. This suggests that electrons at conductance plateaus and between conductance plateaus have different physical nature, thus showing different thermoelectric properties. So to sum up, we measure the electrical and thermoelectric properties of an electron waveguide. We can observe quantized ballistic transport with the existence of Pascal liquid phase in electron waveguide. The thermal power is, in our experiment, explained by the Mott relation, and we observe different temperature dependencies at different conductance value. Thanks for listening.